Since the boom of large language models, the industry has relied on massive, centralized data centers to process billions of parameters. We call these AI factories, and they are highly optimized for one specific task: batch processing massive training datasets over weeks or months. Generating a response for a user is a completely different computational problem than training a model. As the screen says, each request is unique. Each response must be generated on the fly. You cannot pre-compute a live conversation. When you route millions of concurrent, real-time inference requests back to a single centralized hub, physics and economics become a severe bottleneck. The centralized servers cannot parse that volume of unique, real-time traffic without creating massive queues. To solve this, the architecture has to physically break apart. The compute power must scatter outward, moving from an isolated factory into a sprawling web. The strategy of relying solely on the centralized data center to serve global users fails under live generative loads. The physical infrastructure must evolve into a distributed system known as the AI grid. This structural shift is forced by a new class of AI-native applications. Generative technology is moving past simple text chats into multimodal generative agents, real-time voice translation, and live vision analytics. This slide breaks down the demands of new workloads. They require deterministic quality of service, without latency spikes and high bandwidth efficiency. Whether executing live voice translation or augmented reality, these applications demand concurrent processing for millions of users simultaneously. For the end user, the viability of the software rests on two unforgiving metrics: time to first token, which is the total delay before the AI begins its answer, and inter-token latency, the speed at which the subsequent words arrive. Failing to meet these strict latency windows breaks the illusion of real-time intelligence. A voice assistant that pauses for 3 seconds before replying is an application no consumer will retain. The AI grid solves these latency bottlenecks by pushing the compute hardware outward. Instead of building entirely new global facilities from scratch, it leverages the real estate already scattered across the physical world, existing telecommunications networks. This diagram illustrates the macro topology of that distributed network. On the far left, the centralized AI factory remains exclusively for the heavy lifting of initial model training and post-training refinement. The middle tier takes those post-trained models and pushes them outward. The deployment expands from a few large factories into thousands of intermediate nodes located in regional points of presence and central offices. Finally, we reach the edge tier. The grid deploys inference capability directly at millions of local cell sites, placing the actual compute power physically adjacent to the users and devices requesting the data. By utilizing telecom proximity, the network physically moves computational execution away from a distant server farm, dropping it exactly where data is generated and consumed. There is a common misconception that sluggish conversational AI can be fixed by simply installing faster GPUs in the primary data center. Raw hardware speed cannot resolve a structural routing jam. This chart deconstructs the total user latency budget. The delay a user experiences consists of 3 distinct bottlenecks stacked sequentially: network latency, queuing latency, and compute latency. Network latency is a rigid physics problem. It is dictated by the physical distance a signal must travel, the round-trip time, and the capacity limits of the cables carrying the data. Queuing latency occurs when thousands of simultaneous user requests hit a single centralized inference cluster at the exact same moment. The system must line them up and process them sequentially. That centralized queuing penalty alone routinely adds up to 2 full seconds of delay to an AI response. To achieve a natural conversational voice interaction, the absolute total latency budget is under 500 milliseconds. Because queuing instantly destroys that budget on its own. The bottleneck is a topological problem, not a hardware problem. The AI grid targets each bottleneck individually. As this diagram shows, introducing physical proximity by running inference at edge nodes directly shrinks network latency. The data physically travels a fraction of the distance. Next, spreading the request load across thousands of distributed grid nodes entirely eliminates the central queuing penalty. There is no longer a single massive line for processing. Finally, the network mitigates compute latency by deploying small language models, or SLMs. These streamlined neural networks are trained on curated datasets for specific tasks, allowing them to calculate outputs much faster. Matching them to edge hardware accelerates compute time. Applying all three mitigations achieves the outcomes detailed on the right. Voice AI drops below a 500 millisecond response time, and media AI reaches a round-trip time of less than 12 milliseconds. The simultaneous combination of physical proximity, load distribution, and small language models is the only proven architectural method capable of delivering human-grade, real-time AI interactions at scale. To validate these theoretical grid mechanics, we can evaluate an edge deployment by AT&T focusing on AI surveillance. Moving computer vision processing away from a distant cloud and executing it directly at the edge shifts the performance metrics entirely. This chart shows the baseline latency of uncompressed video was 110 milliseconds. Edge inference drops the latency down to 60 milliseconds. Speed is only half the equation. Because the system performs the inference directly at the camera site, it enables massive compression of the video feed. The diagram here illustrates an 80% reduction in data size before anything hits the backhaul network. Edge inference yields faster processing times while simultaneously altering the total physical volume of raw data that must traverse the core network infrastructure. Engineering performance ultimately answers to financial reality. If the unit economics of generating responses fail, scaling an AI-native application to millions of users becomes impossible. The grid model secures those unit economics through a dual-branch logic shown here. It simultaneously optimizes bandwidth efficiency and GPU utilization. Eliminating the central queuing delay we discussed earlier enables the system to handle 4 times higher burst throughput. That immediate clearance of congestion drives up the utilization rate of GPUs across the entire grid. Pushing that distributed utilization up directly collapses the cost of generating answers, resulting in a 76% lower cost per token. The bandwidth math carries equal weight. Converting heavy, raw video data into lightweight metadata at the edge before transmission creates an 83 times lower backhaul traffic load. This volume reduction translates to over $1 billion a year saved in egress fees. Distributing AI infrastructure secures the processing speed required for these applications and establishes the mandatory economic baseline needed to make them financially viable. This forces a final evolution of the telecommunications business model. This chart tracks the shift from telecom providers hosting basic infrastructure as a service upward to platform as a service, and moving directly to providing AI models as monetizable token services. At the peak of that curve sits AaaS, or Agent as a Service. Agent as a Service is a framework where autonomous AI programs capable of executing specific tasks are hosted and rented out to users on demand. It represents the highest value monetization layer sitting directly on top of the distributed grid. Telecom networks are shedding their historical role as passive conduits for connectivity. By physically absorbing the compute layer, they provide the foundational, distributed intelligence grid powering the next era of computing.